Let's move on to the final question in the rectangle geometry section called two tables. So in this problem, you have an axis-aligned rectangle room with the width W and height H. So the lower left corner is the point 0, 0, and the upper right corner in the room is WH. There is a rectangular table standing in this room. The sides of the table are parallel to the walls. The lower left corner is x1, y1, and the upper right corner is x2, y2. You want to place another rectangular table in this room with the width small w and height small h, with the width of the table parallel to the width of the room. The problem is that sometimes there is not enough space to place both tables in the same room. You cannot rotate any of the tables, but you can move the first table inside the room. What is the minimum distance you have to move the first table to free enough space for the second one? So our inputs is first we're given t, which is the number of test cases. Then we're given the width and height of the room. Then we're given the bottom left and the top right coordinate of the table that's currently in the room. And then we're given the width and the height of the new table that we're trying to put inside the room. And we output the minimum distance we should move the first table to fit both tables in the room. And we output -1 if there's no way to fit both tables in the room. Your answer will be considered correct if its absolute or relative error does not exceed minus 10 to the negative 6. And I think this statement is said by looking at this example, which I think throws you off a bit. Because here it says that we move the table that's inside the room, which is the blue table, this distance so that both tables can fit in this room. But that isn't the minimum distance. What would be more optimal is if we just move this table up 1 unit, because then the table would be here, but the new table, this green table, could also fit. So the key thing to notice is that the width and the height of the new table is less than the width and the height of the room. So here, if we know that both of the heights, the sum of the heights of both tables is less than the height of the room, then both tables can fit. Actually, let's just go over the examples that I drew before. So like here, in example 1, the optimal way to move the green rectangle, which in all the examples is going to be the rectangle that is in the room at the start, and the pink one is the rectangle that we're trying to put in the room. The optimal way to add it would to just move this green square up 1. Well, actually, no, that's not the case. The optimal way would actually be to add the pink rectangle at the top over here, because there's enough space. But in this case, yeah, that's a good point. Let me change this so that can no longer be true. So in this case, now the most optimal way would be here, would be to move the green rectangle that is currently in the room up 1 square. And by just moving it up 1 square is more than enough. There's no reason to move it to the right, and that's because we know the width and the height of the new table is within the dimensions of the room. So if there's enough width, so in this case, the sum of the heights, which is going to be this height plus this height, is less than equal to the height of the room, which means the height of both tables can fit in this room. And the width doesn't matter, because once we move this table up 1, which we did here, we moved this green rectangle up 1, we have the entire width with the correct height so that this table can fit. So it's guaranteed that this new table will always fit. Okay, so the first thing to check is, so now we realize that we only have to move in one, we only have to move the rectangle in the room in one direction. We either move it along the x-axis or the y-axis. So that's why we first check if we can fit both the widths of the two tables in the room. I like, and then we check the same for the heights. And if possible, we now need to see by how much we move. So let's take a look at this example. Let's say currently we have a table that's 4 by 4 in our room, and we want to add a new table with a width of 4 and a height of 3. So since we only care about the width in this case, we can we can either add this new table to the left of the room or to the right of the room. Here, if we add it to the left of the room, we see that we have to move the green table by 1 because there's an overlap in of 1 width. Whereas if we add it here to the right, there's an overlap of a width of 2. So our answer here would be 2. So how do we get these numbers? So if we look at the crosses, it's these points. So the way we find these points is the first cross here. That is the width of the table that we want, which is just going to be the small w. And then this small x, since we're only looking at the width, we only care about the x coordinate. And so this is the same as this, which is the bottom left corner, which is the x1 coordinate. So this is how we find the distance. The next one is if we're looking at placing the new table on the right, this point is the same as the top right corner x coordinate, which is x2, and then we have to minus from this point. And what this point is if we just look at the pink rectangle, it's the width of the entire room minus the width of this new table, which is a big W minus small w. And yeah, and the only case where either this or this is going to be negative is if there's already enough space for the new table to be in this room. Right, so for example, just do this quickly in like orange. If we had a 1 by 1 table here, we know there's enough space here. So if we look at so linking this back to w minus x1, because we're adding this to the left of the old table. Here the width is going to be 1 and x1 here is going to be 3. So this is going to be less than 0. So, but in this case, we actually don't have to move anything at all. So what we want to do is find the maximum of 0 and this value. And the same thing for here, maximum of 0 and this value. Because if the value is ever less than 0, then we know there's enough space for the new table to already exist in the room. And for height, it's the exact same thing. So except for height, it's going to be height minus y1 and y2 minus height. So coding this up will look like this. So we create the width and the height of the room, the width and the height of the new table we're going to enter, and we create a rectangle called table. And then we read in the width of the room, the height of the room, the table's bottom left and top right corner, and then we read the table's width and the height. So initially, we set the answer to a really big number because we aren't sure if there's an answer, and we always want our answer to be the lowest possible number. So if we just find the minimum of our current answer and any other answers we find in the future, then that's the way we find the smallest possible answer. So we first do our check. Can the width of the new table plus the width of the table currently in the room, is that less than or equivalent to the width of the entire room? If that is true, then we know that both tables can fit in this room. So now it's an option of, do we add this table to the left or the right? So here, this is when we add it to the left, and when we add it to the right. And then we max with 0 to check whether there's already enough space. And we do the exact same thing with the height. And then at the end of this, if the answer is still infinity, it means that both this condition and this condition was false. And therefore, both tables cannot fit in this room. So we have to output -1. If not, we would have calculated an answer that's less than infinity, because at least one of these conditions was true, which means that either widthwise or height-wise, both tables could fit in the room. And so therefore we have an answer for sure. So we just output the answer. And yeah, this works by here. Just show. But yeah, as shown, it's accepted with the exact same code. So voila.